Hello Mr. Mark and all of my friends. We are from Group 4 and we are going to present our presentation. Enjoy!
So, in this slide, we talk about what is an experimental design. An experimental design is the general plan for carrying out a study with an active independent variable. An experimental design refers to how participants are allocated to the different groups in an experiment. Type of designs include repeated measures, and then independent groups and match pair designs. The next slide we have uniqueness of experimental research. Experimental research is unique in two important respects. The first one is only type of research that attempt to influence a particular variable. And then the second one is best type of research for testing hypotheses about cause and effect relationship. And then in this slide we have experimental design may be classified according to the number of independent variables. The first is single variable designs. A single variable design has two manipulated independent variables. And then single variable research focus on a single variable rather than a relationship between variables. And then the second one is factorial design. Factorial designs have two or more independent variables, at least one of which is manipulated. Factorial designs systematically and experimentally manipulate multiple components or factors of interest. Indeed, factorial designs are commonly used to test the rule of different factors simultaneously in experimental psychology. And then classifying experimental designs. There are three basic types of experimental research designs. The first one is pre-experimental designs, and then the second is true experimental designs, and then the last quasi-experimental designs. So, what is pre-experimental designs? Pre-experimental designs are research schemes in which a subject or a group is observed after the treatment has been applied in order to test whether the treatment has the potential of cause change. And then, what is true experimental designs? True experimental designs is a type of experimental design where the researcher randomly assigns test units and treatments to the experimental groups. Examples of true experimental designs are pretest, post-test control group, and then post-test only control group, and Solomon 4 group. And then what is quasi-experimental designs? So, quasi-experimental design like a true experiment. A quasi-experimental design aims to establish a cause and effect relationship between an independent and dependent variable. However, unlike a true experiment, a quasi-experiment does not rely on random assignments. Instead, subjects are assigned to groups based on non-random criteria. And then, types of pre-experimental designs. The first one is one-shot case study design. One-shot case study design is a single experimental group is exposed to a treatment and observations are made after the implementation of that treatment. And then the second one is one group pretest post-test design. One group post-test pretest designs is the simplest type of pre-experimental designs where only the experimental group is selected as the study subjects. So in this slide we have advantages and disadvantages of pre-experimental designs. The advantages are is a very simple and convenient design that helps the researchers to conduct studies in natural settings. And then it is most suitable for beginners. And then for the disadvantages is considered very weak experimental design to establish causal relationship between independent and dependent variables because it controls no threat to internal validity, and then it has a higher threat on internal validity of research. And then the last is may have selection bias, which is very serious threat. And then the next slide we have true experimental research design. The true experimental research design relies on statistical analysis to approve or disapprove a hypothesis. The classification of true experimental design include the first is the post-test only control group design, and then the pre-test post-test control group design, and then Solomon 3 group design, and then Solomon 4 group design. So, what is the post-test control group design? The post-test control group design is a type of true experimental design where the test units are randomly allocated to an experimental group and a control group. The experimental group is exposed to treatment and both groups are measured afterwards. And then, what is the pre-test post-test control group design? The pre-test post-test control group design is a type of true experimental design where test units are randomly allocated to an experimental group and a control group. Both groups are measured before the after experiment group is exposed to a treatment. And then what is Solomon 3 group design? In experiments with these designs, researchers use two comparators. One of the comparison group was measured before the experiment was carried out. And then the three groups were randomized using the principle of random assessment. He took measurements before and after the intervention treatment was given to the experimental group. And then, what is Solomon 4 group design? The Solomon 4 group design is a research design that attempts to take into account the influence of pretesting on subsequent post-test result. Some research design include a pretest which is taken before exposure to a treatment, and a post-test which is administered after exposure to a treatment. In this slide, we have advantages of true experimental design. The first one is the result of a true experimental design can be statistically analyzed, and so there can be little argument about the result. And then it is also much easier for other researchers to replicate the experiment and validate the result. And then the last is for physical sciences working with mainly numerical data, it is much easier to manipulate one variable. So, true experimental design usually give a yes or no answer. So, here the disadvantages of true experimental design. The first one is human error also plays a key role in the validity of the project as discussed in previous modules. And then it may not be really possible to control all extraneous variables. And then the health, mood, and life experience of the test subject may influence their reaction, and those variables might not even be known to the researchers. And the last is the research must adhere to ethical standards in order to be valid.
Next, we move into the factorial design. In factorial designs, these designs are presented thus far have been the classical single variable designs in which the experimenter manipulates one independent variable x to determine of its effect on a dependent variable y. A factorial design is one in which the researcher manipulates two or more variables simultaneously in order to study the independent effect of each variable on the dependent variable, as well as the effects caused by interactions among the several variables. This also may well be that the effectiveness depends on a number of variables such as the age, ability level of students, the personality of the teacher, subject matter, and so on. For example, may be more effective with below average students than with bright ones. This one, a classical one variable design, would not reveal this interactive effect of method and intelligence level. In this part, there are the illustration where it has the example of the simple design, where this is the symbols of factorial designs of the 2 times 2, which is as right as 2 by 2. This design has 2 factors and each factor has 2 levels, like in this illustration. This is the table 11.1, where it is the example of a factorial designs. In this table, it shows the 2 by 2 factorial designs. The aptitude factor has 2 levels, high and low. The other factors, instruction method, also has 2 levels, like in the example A and B. The researcher randomly selects 60s from the high aptitude group and assigns 30s to method A and 30s to method B. This process is repeated for the low aptitude group, where the teachers are also randomly assigned to the groups. In a 2 by 2 design requires 4 groups of subjects. Each group represents of a combination level of one factor and level of the other factor. The scores in the 4 cells represent the mean scores of the 4 groups on the dependent variable. The science achievement does, in addition to the 4 cell scores representing the various combination of treatments and levels, there are 4 marginal mean scores, 2 for the columns and 2 for the rows. The marginal column means are for the 2 methods or treatments, and the marginal row means are for the 2 levels of aptitude. A factorial design also permits the investigator to assess interaction between the 2 independent variables, that is, the different effects of one of them at different levels of the other. If there is an interaction, the effect that the treatment has on learning will differ for the 2 aptitude levels. If there is no interaction, the effect of the treatment will be the same for both levels of aptitude. Looking at an example of table 11.1, you can see that the method A mean is higher than the method B mean for the high aptitude group, and the method B mean is higher for the low aptitude group. Thus, some particular combination of treatments and levels of aptitude interact to produce greater gains than do some other combinations. This is the illustration method and aptitude level. In figure 11.5, the researchers randomly assign subjects within each aptitude level to one of the 2 methods. The researcher administers achievement tests and records the scores for every subject. This is the example of factorial designs in table 11.2, where we can see there are the aptitude and treatment and mean. The factorial designs can be extended to more complex experiments in which there are a number of independent variables. The numeric values of the digits indicate the number of levels for the specific independent variables. There are 3 independent variables with 2, 3, and 4 levels, respectively. Such an experiment might use 2 teaching methods, 3 ability levels, and 4 grades. Theoretically, a factorial design may include any number of independent variables with any number of levels of each. However, when too many factors are manipulated or controlled simultaneously, study and statistical analysis become unwieldy and some of the combination may be artificial. The number of groups required for a factorial design is the product of the digits that indicate the factorial design. The advantages of the factorial designs are that it accomplishes in one experiment what otherwise might require 2 or more separate studies, provides an opportunity to study interactions that are often very important in educational research, and provides a more powerful test of hypotheses. Other randomized experimental design. The essential feature of these designs is that they compare separate groups of subjects in order to determine the effect of the treatment. When the independent variable is manipulated in this way, we have what is called a between-subject design. Like for example, a researcher who compares reading achievement scores for students taught by one method with scores for an equivalent group of students taught by a different method is using a between-subject design. This is the type of a design in which a researcher observes each individual in all of the different treatment is called a within-subject design. It is also called a repeated measure designs because the researcher repeats measurements of the same individuals under different treatment conditions. The main advantage of a within-subject design is that it eliminates the problem of differences in the groups that can confound the findings in between-subject research. Next, we move into another advantage, and its advantage of within-subject designs. The advantage of within-subject design is that they can be conducted with a fewer subjects, and the disadvantage of this design is the carryover effect that may occur from one treatment to another. To deal with this problem, researchers typically arrange for the participants to experience the different treatments in random or counterbalance order. Next, we move into the quasi-experimental designs. Quasi-experimental designs are similar to randomized experimental designs in that they involve manipulation of an independent variable, but differ in that subjects are not randomly assigned to the treatment groups. Because the quasi-experimental design doesn't provide full control, it is extremely important that researchers be aware of the threats to both internal and external validity and consider these factors in their interpretations. In Design 9, non-randomized control group Pretest Designs is one of the most widely used quasi-experimental designs in educational research. This is the example of Design 9 non-randomized control group and Pretest Design, where you can see it is similar to Design 5, but with one important difference. Design 9 doesn't permit random assignment of subjects to the experimental and control groups. There are some possible internal validity threats, however, this design doesn't control threats resulting from an interaction of selection and some of the other common threats. There are, first, interaction of selection and maturation. The problem arises when the two groups differ in their propensity to maturation. If one of the select group is more subject to maturation than the other, you have an interaction of selection and maturation to threaten internal validity. In selection and maturation interactions, it can be a particularly difficult problem when volunteers are compared with non-volunteers. Like for example, let us say you offer an after-school reading improvement program to those who wish it. Reading pretest means show no difference between those who volunteer for the after-school program and those who don't. If the post-treatment scores show greater gain for the treatment group than for the control group, you cannot confidently attribute the greater gain to the treatment. Sometimes it is quite possible that students who were willing to participate in the after-school program were more concerned about their reading, or their parents were more concerned about their reading, and then they were therefore more likely to show greater gain in reading whether they received treatment or not. And second, interaction of selection and regression. A selection-regression interaction could be more occur in this design if you drew the groups used in the study from population having different means. And the last, interaction of selection and instrumentation. In this part, this characteristic could result in changes occurring for one group that apparently don't occur for the other. The gains are limited by the difference between the post-test ceiling and magnitude of the pretest scores. Like for the example, if a student answers 92 items correctly on a 100-item pretest, these students can only gain 8 points on the 100-item post-test. However, a student with a score of 42 on the pretest could make a gain of 58 points on the post-test. The ceiling effect does restrict students with high pretest scores to a low change score. Maybe they may have improved greatly, but the instruments cannot show the gain.
The next is Design 10, Counterbalance Design. Counterbalance design can be used with intake class or the whole class and rotates the groups at interval during the explanation. So in counterbalance design, all groups receive all treatments but in different order. So it involves the series of replication, and in each replication the groups are shifted so that at the end of the experiment each group has been exposed to each X, but in different orders. Teachers could use this design to compare the effectiveness of two methods of instruction on learning. So the comparison of the column mean score at the bottom of the table, it indicates the effectiveness of the methods. And the mean score also indicates the performance of the cell groups on the dependent variables under the treatment represented by the column. Design 10 overcomes some weaknesses of Design 9, one of which is it provides an opportunity to rotate out any differences that might exist between the groups. The weaknesses of Design 10 is that there may be a carryover effect from one X to the next. So teachers must be careful so that they will only use this design when the experimental treatments do not have the effect from one to another. And another weaknesses of counterbalance design is the possibility of boring students with the repeated testing that the methods requires. The next is time series design. Time series design is divided into two: Design 11, one group time series design, and Design 12, control group time series design. In Design 11, one group time series design, it used to study the effects of a major change in administrative policy on disciplinary incidents. It involves periodic measurement on one group and set the introduction of an experimental treatment into this time series of measurements. Design 11 is similar and has certain advantages over Design 1. It uses before and after measures and lacks a control groups, and the repeated testing provides a check on some common threads to internal validity. Statistical interpretation can be a particular problem with time data. The tests are not appropriate with time design because they assume that observations are independent of one another, but time series data are typically correlated with one another. In Design 12, control group time series design, it will measured at the same time as the experimental group but will not experience the X treatment. Design 12 is the extension of Design 11, but it includes a control of group. Design 12 overcomes the weakness of Design 11, which is failure to control history as a source of extraneous variance, and the control group permits the necessary comparison. Validity problems with experimental designs. So here is the summary of some sources of invalidity in the one variable experimental designs, whether the factor is controlled or it lacks of control. The number 1 to 12 is the designs that we have learned, and the name of the designs are listed at the bottom of the table. I also provide more information, especially about quasi-experimental designs. You can check it in the description box. The next is single-subject experimental design. Single-subject experimental design is a type of experimental design with a unique feature. The sample size is just one or composed of a few participants who are tested as one unit. So there can be random assignments or use of control groups. The participants serve as both the treatment and the control group. In single-subject experimental design, the researchers measures the participants' behavior twice. The first one, when the treatment is not presented, or usually we call it baseline periods. And the second one is when the treatment is presented, and we call it treatment periods. The baseline periods referred to by the letter A, and the treatment period by the letter B. These are the two major approaches of single-subject experimental design, the baseline period and the treatment period. Single-subject design are the extension of the quasi-experimental one-group time series design, or the Design 11. And the two most common are the ABAB and the multiple baseline design. What are they? ABAB design. It consists of a period of no treatment or baseline A during which the behavior is repeatedly measured. For example, we are going to see how many times a student with cognitive disability leaves her seat. So the first one, we use the baseline or phase A, or the pre-treatment assessment. The pre-treatment assessment serves as a control period with which the treatment will be compared. After we got a stable picture of pre-treatment behavior, the treatment, or phase B, is initiated. The treatment is like giving privilege or giving reward. After some time, the children can stay seated. Further experimental control is achieved by a second A phase. Second A phase is a reversal of treatment reinforcing a behavior incompatible with the desired response. The ending of the second A phase has the drawback of leaving the client in the same state as before the experiment started. And to add more strength by replicating the procedure, the treatment B, or the second B phase, is instituted. The key element of ABAB design is the return to former levels of behavior when the baseline condition is reinstated. And this design has the clinical advantages of counting any improvement made without returning to less desired behavior. Multiple baseline designs. The observations of multiple baseline designs are made on several participants, different target behaviors of one or more subjects, or different situations. There are three basic designs. The first one is multiple baseline across participants design. It is applied to similar behaviors to the same individual in the same setting. The second one is multiple baseline across behavior design. It is two or more behaviors of a single student are examined. And the third one is multiple baseline across setting designs. It is applied to the same behavior to the same individual in different settings. Here, the treatments affects different behaviors specifically. For more information about multiple baseline design, I provide a video of explanation in the description box. The last is comparing of single subject and group designs. Both of the goal is to establish as unequivocally as possible the connection between the manipulation of the independent variable or the treatment and the effect on the dependent variable or the behavior. First, group design. It used random assignment of subject to experimental or control group eliminates many rival explanations of differences observed after the treatment, while single subject design used another method to establish credibility. Single subject design to bypass one source of error of group designs, or it is called inter-subject variability. The well-design of single-subject research can meet the criteria for internal validity. That's all from us. Thank you very much everyone for listening.